Hey, good morning again, gang. Here's a look at that wall writing video that we just take a look at. I just think that's amazing. You could see that motorcycles were doing it, those little cars were doing it. Um, I think you could do it on lots of different things. It'd be pretty scary. You'd have to practice it first, but let's take a look and see why it's possible. So we're just going to do an estimate and take a look at the speed that would be needed to stay on the wall. And what we're going to use here is what we've learned about centripetal forces. So first thing you do, always remember, is you're going to do an FBD. Now, I took the diameter of that wall. I looked at a car and I kind of figured out what the distance of a car is, and I figured it's about 3 and a half cars apart. So the diameter is, I took about 35 feet. So I'm going to estimate the radius at about 17 and a half feet. Okay. So I looked up tires and pavement. And of course, they were riding on, I think it was like bamboo or something, but let's say it's pretty close. Let's take the mu to be 0.7. That's what rubber tires would be on the road. So, but you'll see there's enough play in this where we could play around with those numbers and even make mu a little less and r a little less or bigger, and it's going to end up being, I think, pretty reasonable. So let's take a look at our free body diagram and how we might approach this. So if we draw our FBD, we've got a car riding on a wall, could be a motorcycle, whatever, and our FBD, remember that the surface of the wall is going to be pushing inward on the car. What's holding the car from sliding down is got to be the force of static friction, upward. Static friction between the tires and the road because we're not slipping up or down. And of course, the force of gravity is going to be straight down. So it's a pretty simple FBD. And what we do is we create our inward centripetal direction and our perpendicular direction y. So remember, plus c is inward and plus y would be upward at this point. So we make our t-chart. Centripetal force is only the normal force. Our y direction, we have a plus static friction upward and gravity downward. Of course, it's not going up or down, so there's no acceleration in the vertical direction. All right, so from here on out, it's pretty straightforward, actually. We have our equation in the centripetal direction, our equation in the y direction. And in the y direction, we can see that we would just have static friction minus gravity equals 0. We know that static friction is mu times the normal force. Aha, a link to the centripetal direction. So if we solve here, we can find out that we can express mu times the normal force equals mg. Or solving for a normal force expression, it should be the weight divided by mu. So all this information comes from what we know in the y direction. Now, why are we solving for the normal force? Aha, because that's in the centripetal direction, which is going to allow us to find the velocity. So let's come back to our centripetal formula, realizing that the normal force is the only force in the centripetal direction in this case. So that has to equal our mass times centripetal acceleration. So we can now substitute what we've learned from the y direction into our centripetal formula. And lo and behold, when we do that, for the normal force, we get mg over mu equals mv squared over r, and now the fun really begins. Look at this. Mass cancels again. So it doesn't matter if you're on your 10 speed, that would be kind of scary. If you're on a motorcycle, I think that's really scary, or your car, even scarier, right? The mass drops out. So it should be the same speed for pretty much all the riders. Now, you could certainly go faster than the minimum speed here. This is just the minimum normal force, right, to keep you on the road. The faster and faster you go, well, the better and better it is. So we're just solving for what the minimum speed would be here, all right? And the minimum speed would be the same for any vehicle because the mass drops out. All right, so that's pretty cool. So we end up with g times r over mu equals v squared. We just kind of keep going here. And we get the square root of rg over mu equals v. And so I'll substitute in my assumption. So I assume, again, a diameter of 35 feet. We use g in English units again. R is 17 and a half feet and mu is 0.7. And we come up with a velocity of 28.3 feet per second. So what would that say on our speedometer? Well, here we go. 19.3 miles per hour is all you would need so that you could ride on that wall. I think that's pretty amazing myself. I think it's incredible. I would have, my gut instinct would be not to drive my car on the wall, but it looks like I could do it. My Tahoe would be kind of awkward, but wow, it's kind of tempting. So the idea would be people have figured out how to do this, and it's kind of cool. So again, you can certainly go faster than that, and that would be even safer from sliding down the wall. All right, there you go. Hope you enjoyed that.